Any others? Okay, give the major substitution product and the major elimination product. Hydroxides the nucleophile substitution, replace the leaving group. SN1 or SN2? SN2 is strong nucleophile, so it's going to be direct displacement of the leaving group inserted. No rearrangements possible. Inversion. So this here is, whatever that is, inversion can be shown if we keep the backbone the same with the bold. That looks like it's S. This should be R. SN2 product looks good? How we do? Major elimination product, but we're doing E2 because we have a strong base. We'd like to get the thermodynamic product if we can. This is not a steric linear base, so we should be able to do that. So we should be able to extract HA and give the tri-substituted double bond. If we put double bond in over there, it would only be di-substituted. Tri-substituted could be that, or they could have an isomer. We show the Newman. We rotate it so the H and the Br are anticoplanar. When we do that, we see the ethyl and the phenyl are on the same side. And so the ethyl and the phenyl are on the same side. So it's that alkene, and that alkene is actually Z. How do we do? I imagine not everybody got that right. I don't know why I imagined that. But for those who did not get that right, why did you not get it right? Questions about it? No questions? Okay. Give the major, let's see. Give the major product of the following two-step reaction. Consider stereochemistry. We have this compound here with sodium hydroxide. It's going to deprotonate the more acidic OH. So we're going to get the O minus. Now we have a good nucleophile. We come in here and we can displace the Br. And we get the O binding to that carbon, the deuterium. O binding to the carbon, the deuterium. We're doing inversion, so this is R. This should be S. You could show it like that, or you could also show it like that. Either way you want to show it, they're both S. Under my hand used to be what before we displaced it? What did we used to be bromine? But now we have the nucleophile there, right? The nucleophile replaced the leaving group. Questions about that one? Mark?
So why would it use the other OH?
Well, we're only using one equivalent of hydroxide, one molar equivalent. Which one's more acidic, this OH or this OH? The phenol or the regular alcohol? Phenol is more acidic, a million times more acidic because the resulting anion would be resonance stabilized. Compound we want to go E2 the fastest would be the one circled. Why? Well, first off, you see they're all kind of analogous. These are the same except bromine and iodine. Which one's a better leaving group? Iodine. Over here, the iodine and the two methyls are cis. They're all down. Here they're trans. The more important thing is the H that gets eliminated in the elimination. Here and here, what's their alignment or their stereochemistry? They're anticoplanar. But over here, the H and the I are not anticoplanar. They're syn-coplanar. Which is better, anti or syn? Anticoplanar is going to be easier to eliminate. Questions? Iodine is a better leaving group, anticoplanar preferred. Any questions about that? We did go over iodine bitter leaving group, right? We did go over anticoplanar preferred, right? So why did you miss it? You forgot what? No, when you eliminate, the H in the leaving group have to be anticoplanar, right? You're eliminating the HI. Put the double bond in here, right? We're doing E2 elimination. You eliminate HX, HCl or something. In lab last week, you eliminated HBr twice from the dibromide. Using appropriate arrows, show mechanism. It looks like the OH has left the building. Everybody agree the OH has left? How do you make OH a good leaving group? Protonated. Do we have any strong acid available? Yes, phosphoric acid. We can protonate the OH. We have I minus here. This thing, I minus can attack. Kick that off. But then we would have I here. That would not be that product over there. What else could this do? Leaving group could just leave. It could just ionize. We give this cation. I minus could attack here, but that would not give that product. Do a hydride shift. Give this cation. Then we could do resonance to give that cation. And now iodine attacks that plus to give final product. How we do? How we do, guys? No? Questions? Questions? Questions about this problem? What was the stumbling blocks?
I didn't see the hydride shit.
So what did you do here? Did you get to this cation?
I got to there.
What did you do?
I got up to the point where I can ionize it, but from there I didn't see the fact that I don't have the hydride shit.
So what did you do from here?
That's as far as I got.
Okay. You got to consider your options. What are the options here? I minus could add here. Could you show I minus adding here?
Yeah.
Sure. Would that give that product? No. So what else can you do with the cation? What are cations prone to do? Rearrange. I think that's about the 18th time I said that. So you got to say, what are the options? So rearrange, okay? Do you want to move cation over here? Would it be reasonable to put cation here next to the pi bond so it would be resonance stabilized? So you can do that and get to this, resonance. Then you can do resonance in your home because now you see this and it's there. Carbocations like to rearrange to more stable carbocations. Always be alert for that. If you were asked to show a more stable carbocation here, what would you show? Wouldn't you show this one through a rearrangement? So that's the thinking. Okay, I've got a carbocation. I don't want to add I minus. What can I do here? Always consider rearrangement to a more stable carbocation. And hopefully you would see that this is how you rearrange to a more stable cation. Everybody see that this is more stable? It's resonance stabilized. Now if you look at the product, you somehow have to get the pi bond here in the middle. That could be another kind of clue. But the most important probably is, what can you do here? You don't want to add I minus because that's not the final product. You've got a carbocation. What do you want to consider? Carbocation rearrangement. Not to just any cation, but to a more stable one. So at that point, did y'all all consider rearrangement to a more stable carbohydrate? I see some saying yes, but I think many did not. Take home message, whenever you have a carbocation, what do you want to look out for? Always. He will be posted upstairs, third floor, sign call. Let's finish up the current handouts. Lab sheet for the, not shaken, not stirred, but double E2 elimination, next James Bond movie. See, I'll follow 15. We'll be due Monday week. Come back. It's an answer sheet, right? We'll do Monday when you come back. The test. Somebody want to move it to when?
Wednesday.
Okay, we'll move it to Wednesday. That'll be the Wednesday after you come back.
What about Friday?
Do what?
Before the Friday.
Friday's the last day of class. Can't have a test on last day of class.
Why not?
It's some rule somewhere. Because it has to be passed back. We can consider moving it aside. Today we'll finish this up. On Monday when we come back, we'll cover UV Viz. That's chapter 17. It will be our third type of spectral analysis. IR, mass spec, UV Viz, chapter 17. UV Viz. UV Viz.
When do we get the lab the next one?
Because it's the last day, let's don't do a lab on next week. Lab's done, no more labs. We will check out next Thursday and Friday. Is that okay?
Yeah.
If you feel like you're getting gypped, I'll give you a lab to do on your own. I'll check out on Thursday and Friday. Next week, yes. No, let's see, finish up the current handout. E1, E2. E2 on the front, synthesis of Tamiflu. It's a miscellaneous thing. Heat favors elimination. For example, on the quiz, the very first one said give a substitution and elimination product. What if you wanted this E2 product to be the product and you didn't want that? How would you do the reaction to make the E2 the favorite product? You would heat it very hot, high temperature. By heating, you're saying, let's magnify the entropy term. And if we eliminate, elimination is breaking one molecule into two. Substitution is not. You're just replacing something with something else. Thus, if you want the SN2, how would you do this reaction? What's the opposite of heating?
Cold.
Cold, or maybe at room temperature. And it may be slow, but the more you heat, the more you're going to favor elimination because the more you're magnifying the entropy term in your Gibbs free energy. That's what we're talking about there. You can control the outcomes, but you have to understand how. Maybe you won't get 100% elimination, but you'll get more than not. Involvement of a good nucleophile will favor substitution. We talked about that. Third, I think this is new. It's not actually that new. A more sterically hindered base will favor elimination over substitution. We've already kind of said this. Substitution requires backside attack. It has to be very precise. Come in there backside. The more sterically hindered, the more it's going to be difficult. We said that SN2 is governed largely by what? steroids. Thus, what if you wanted to do this reaction? What are we doing here? Substituting or eliminating? We're eliminating. So really, the reagent you use is not going to be incorporated into the molecule. The reagent you're using is going to act as what? A base to extract the hydrogen. Which one would be best to do this? If you wanted to say, hey, I don't want any substitution, I just want elimination. Sterically hindered. How about this O minus sodium plus here? With these wings on it that are pretty big. They're not directly on the oxygen, but they are there. Keep it from, it's going to have a tough time coming in backside with these wings on there. Somewhere in the substitution page it says how T-butoxide is very useful for E2 elimination. It won't do substitution that well. If you use sodium hydroxide, you can. We used it last week in lab to double eliminate potassium hydroxide. There is a chance that hydroxide might just do a substitution. You get the OH here instead. Less of a chance with the sterically hindered base. Now, all these are strong bases, including ammonia, because it's an sp3 nitrogen. What mechanism is this? If you use any of these bases, what mechanism are we doing here? Obviously, we're doing elimination. We have two mechanisms, you know. E1 or E2?
E2.
E2. This would be E2. This is right there. Could you do this another way? Could you do this E1? E1 involved, this is ionizing, making a cation. What would you use? How would you do an E1 here? You wanted this to do E1. Somebody tell me. If I gave you that star material and said, go to lab, do an E1, what would you do with it? What reagents would you use? Camille? A weak base. What weak base you want to use?
Water.
Okay, we could show water. That gives a weak base, certainly not a strong base. Let's think practically though. Do you think this is going to be soluble in water? It's an organic molecule with just carbons, hydrogens, and a bromine. It does have a dipole, but you got a lot of carbons there with only just one dipole. No hydrogen bonding. Not going to be soluble in water. That's going to be like oil and water heating. It's just not going to mix well. How about something else? What else other than water? Why do you want an acid? I mean, we're really not going to be protonating anything, and an acid is certainly not a weak base. I mean, it is. It's the weakest of weak bases. I don't know why acid would, it's not an OH. How about instead of water we use ethanol? I mean, the only difference between water and ethanol is ethanol's got an R group, water doesn't. It's still the same idea though. It's going to be a weak base. Basically just solvent. Water and ethanol are both solvents up here. It's just if you use ethanol, this will dissolve in it. Ethanol heat. Why heat? Why would I propose heating this?
Because it's going to do substitution.
I would look back at number 1. Heat favors elimination, right? Heated in ethanol. What mechanism would take place? This would be an E1. What mechanism would I thus be hoping that would occur? What would be the first step? Just ionization. Get this carbocation, Br minus. Now what? Beta hydrogen here. Either ethanol or this could take the H. The fast step. Really, when you do an E1, you don't even really need a base. The leaving group can act as the base after it leaves. An E1 really doesn't even need a base. The leaving group can act as the base. And in this scenario, you would make this plus what?
H2O.
Plus HBr. Okay? So that would be an E1. If you want to do an E2, I would use a sterically hindered strong base, concerted elimination. If you use something like one of these, you might get a substitution product by an SN2. Okay. G, I don't remember F. Were we under F? Like we were.
Yeah.
G. Clever ways to make the ionization of an alkyl halide to a carbocation easier. How do we make an OH? Basically, how do we make something a better leaving group? How can you make a halide a better leaving group? It's not really going to be protonated. To make an OH a better leaving group, we protonate it. You usually don't protonate a halogen with acid. It's just, well, go to lab and try it. It ain't going to work for you. So we have to figure out why. With halogens, we have not done anything with a halogen to date. We've just said it just leaves. We made an OH a better leaving group. How can you make a halogen a better leaving group? That's really what we're doing here. Not a proton acid, but a Lewis acid is often used for halogens. We'll use it here, we'll use it in organic too. For example, you want to react this with water. I'm showing an elimination product. I don't see any strong base, so this must be E1. What's the first step of this mechanism? Ionization. That's the determining step, right? How can we make the ionization of this alkyl halide to the carbocation faster? Use a Lewis acid. A common Lewis acid for halides is silver ion. This is Ag plus, nitrate minus. Silver nitrate is a common source of Ag plus because it's soluble. Remember your solubility rules, something like silver bromide, silver carbonate, they're not soluble. Just about all nitrates are soluble. That's why silver nitrate is used here. Solubility. Silver nitrate will dissolve in water. Your halogens and your silver really love each other. Now this is sort of a little bit of hand waving because it's I'm going to show it like this, but it may not be exactly like this. This guy is going to coordinate with that silver. I can even show it, perhaps the Br bonded to the silver. Silver is now neutral. The bromine is what? The bromine is plus. Because this is a very strong attraction. As these electrons will start bonding to the silver. At this point, this is a lot like a protonated OH. How do we make oxygen a better leaving group? We protonate it. But really, what are we doing? We turn the oxygen into a positive. Bromine is positive through coordination with the silver. Now it's like, okay, I'm out of here. Boom. I'm going to go here. And what do we get? We get the desired carbocation plus what? AgBr, which is silver bromide. If you remember your solubility rules, that's not soluble in water. This precipitates. And the precipitation of this is a driving force. So this complexes and ionizes off and precipitates, but there you go. It helped form the carbocation. When you did the shaken not stirred, you treated your product with silver nitrate, and what did it do? It gave it precipitate. That was silver, in that case, chloride. Now we didn't worry about the fate of the carbocation in that test. We were just looking for, will it form a precipitate? Ionizable halogens will form a precipitate of silver halide with silver ion. Is that an ionizable halogen? Yes, we can make carbocation there. So, take home. We didn't protonate the bromine with a proton acid. We coordinated with a Lewis acid. What's the definition of a Lewis acid? It accepts a lone electron pair. Accepts an electron pair. You see how the silver is accepting the lone pair of this bromine? This lone pair, this used to be a lone pair, but now the silver accepted it, it's now bonded to it. Coordinate, come together, associate, maybe bond. Pretty much analogous to an equal bond. But bond means usually covalent bond. A hydrogen bond, you could say the hydrogen coordinates with the oxygen lone pair. It attracts, it associates. It's a little bit more generic term than bond. Usually bond implies covalent. Silver ion. In organic 2, we'll use aluminum as a Lewis acid for halogens. Similar to how proton here. See if we use this, HF, first step would be what? Coordination of the oxygen lone pair with the H to make the protonated there. Similar idea. With halogens, you use Lewis acids, not proton acids. Because of these silver precipitating, we can use it as a chemical test. We can ask questions like this. Which compounds would give a precipitate when treated with silver nitrate? Two-part question. What's the answer to the first part? Which compound below would give a precipitate when treated with silver ion? I heard all of them. Anybody else?
Not the first one.
Hey.
right?
The bromine, the second bromine, is bromine compound.
That one will, yes. What other ones? The third one, yes. Any other ones?
That one too.
And
That one, yes. Those three. Why not this one?
not a tetrahedral. Not a
It's
tetrahedral
next
carbon.
Somebody said what?
Not a tetrahedral carbon.
Not a tetrahedral carbon. I'll refer you back to the on both sheets, the major heading had tetrahedral carbon in there. The chemistry we're doing of leaving groups, the leaving group has to be on a tetrahedral carbon. Everything we're doing in this here. The leaving group has to be on a tetrahedral carbon. We typically do not make carbocations on sp2 carbons. We do not want to make carbocations. You also are not going to do an SN2 backside attack there. No chemistry that we've ever done in this course we will do here. Those three, yes.
Can we go back to the alkyl halide? When you, what you drew, you left like a positive charge on where the,
On the bromine?
yeah.
Uh-huh.
How do you then get to the double bond that you have shown in the product?
Well, that's the, you got to complete the mechanism. After it ionizes, you get the plus, right? So then if you want the double bond, something's got to take this H. I mean, water can take it. What did I show taking it in this? NO3 minus, you can show that as a Lewis structure, takes the H, this comes in. This is the fast step of an E1 beta elimination. So it has to take the H with the electrons in it. Of these three, which will give the precipitate the fastest? What's really the question? Which will form carbocation the fastest? That's what the question is. Which one will? If this makes cation, you just get a secondary cation. If this makes cation, you get what?
Tertiary.
Not only is it tertiary, it would also be resonance stabilized. This one would be what? Be primary, but it would also be resonance stabilized. So it would be primary, resonance would make it secondary, so it's primary, secondary with resonance. This one's tertiary. If you do resonance, you get what? Secondary. Which is better? Tertiary, secondary, or primary, secondary? It's going to be your most stable cation. It will form fastest. Number two, for how do you make ionization faster? Talk about making ionization of an alkyl halide faster. Use a polar solvent. You take this with benzyl alcohol and a polar non-nucleophilic solvent, you can get this product here by an SN1 ionization, and this attacks cation. And then something takes the H, like Br minus takes the H. If you try to do this same reaction in a nonpolar solvent such as hexane, probably not going to react. What is the role of the polar solvent? Why does a polar solvent make the reaction work with a hexane and it keeps it from working? Because, what's the first step here? Ionization. What type of solvent is going to favor formation of an ion? Polar. You learned this in Gen Chem, right? When you put HBr in water, what does this do? Ionizes, because water is polar. It becomes H plus Br minus. And of course, you usually show water here and say H3O plus. But what happens if you put HBr in hexane? Does it ionize? No, it does not. It just stays covalent. You have HBr in hexane. Okay, that's what you got. Gen Chem, right? Polar solids facilitate ionization. Why? Because the polar then coordinates to these ions and stabilizes them, hugs them, tells them they're good being ions. Does hexane like these ions? No, hexane treats them like the plague. I don't like you. So the solvent coordination helps stabilize your ions. It helps them form. Polar solvent helps stabilize. You want this. This is your rate determining step, forming this ion. Polar solvent will facilitate it. Non-polar solvent, it doesn't want to ionize. H, different topic. We'll introduce this. Deuterium isotope effect, another miscellaneous thing. The neat way to determine if an elimination reaction is E1 or E2. Consider this reaction. This alkyl bromide treated with pyridine, eliminate. Pyridine obviously took the H, there's your leaving group. Obviously elimination. Is it E1 or E2? Up to now you would say, well, is this weak or strong?
Both areas.
Weak or strong?
Weak.
Well, if you go by what I told you, is it an anion? Is it an sp3 nitrogen? Then you would say weak. And if it's indeed weak, what's the answer?
So it would be E1.
E1. But maybe my sweet way to determine if it's weak or strong was really not, it was borderline. This is borderline. If it's weak, it's kind of real strong of the weaks. Well, do you just want to trust some statement, general statement that the instructor made, or would you like to scientifically prove if it's E1 or E2? hopefully you like to scientifically prove it. Well, here's a way. Deuterium isotope effect.
We can just increase the amount, see if it's a great.
There's actually two ways, yes. One way to do this is do a kinetic study. Because if it's E2, you can double the concentration of your base, and that should increase the rate. But what if you double the concentration of the pyridine and it does nothing to the rate? Sounds like it's E1. Yes, kinetics. This is another thing other than kinetics. Please read about it. We'll mention it next time. Please also give the answers to the things on the last page. In terms of deuterium, there's something about deuterium on the back here. It's important for medicinal chemistry, drug design. And that finishes up the handout. Please be doing problems in the workbook, of course. I may see if SI can be changed to tomorrow. And for next week, also be on Tuesday. I will let you know by email.